All right, let's just do the last 15 questions. Okay, for this matrix, the following is correct. A cube plus. All right, so yeah, there's a theorem that says that okay, actually, first of all, we figure out eigenvalues or something, or you could diagonalize the matrix itself, but there is a lot of work. I guess we'll just figure out the eigen. Yeah, the characteristic is polynomial for this guy. Okay, just do the thing. So we have to figure out anyway, right? If you want to figure out the diagonalization, right? So just do it the proper way. What do you have? Just have what I'm going to do is actually like lambda minus one or something. Yes, lambda minus one. We got minus one over there now. 0, 1. Oh, it's not one. It's negative one, of course. Or you could have been doing negative lambda as well. Yeah, let's not do that. Let's do lambda minus 1. So then you have lambda minus 2, then lambda. So negative 1 over there, and negative 2 is negative 1. This thing, this has determinant equal to 0, right? We are saying just has determinant equal. You know what, actually, instead of lambda, let's say x. Because why not? This determinant is equal to 0, right? Okay, let's just calculate this thing. So also just x over there. Okay, very weird. I mean, we wish we could somehow cancel up some stuff. Right. Isn't there some better way to actually cancel out some stuff? I think not. We just have to actually figure it out, right? Okay, let's just start. So, first what you have is the first diagonal, which is just x minus 1 times x minus 2 times x, which is just x times of x squared minus 3x plus 2. And the second diagonal is just negative 1, is like positive 1, then times of negative 2 is just negative 2. Okay, and then the third diagonal, which is just 0. Okay, then minus the first diagonal, which is just 0 once again. Second diagonal is just this, and that, which is x minus 1. And the third diagonal is this and that, which is just plus x. Awesome. So what do you can just get like x cubed minus 3x squared plus 2x minus 2 and minus 2x and plus 1, right? Which is x cubed minus 3x squared minus 1, that's equal to 0. So this is the characteristic polynomial, right? Um, there's a theorem, I don't remember its name. It's like the something Hamilton theorem. I don't remember its name really. What it basically says is that this matrix A is itself like actually, yeah, this matrix A is a root of this equation actually, right? And yeah, it actually goes into details to show how that happens and everything. Should I give you a proof? No, that's just too much. For now, just know that this theorem exists, which basically says that if this thing is the characteristic polynomial which you use to figure out the eigenvalues. Oh god, this is getting very advanced all of a sudden, right? You could just actually, like actually calculate what a power 3 should be or something like that, but this is just a much faster way, and if you really want to do it the proper way, this is the proper way, right? What it basically says is that a power 3 minus 3a square and its identity matrix equal to 0, right? So just replace every constant by the scalar identity matrix. You know the thing, right? You don't know the thing. It's only I who know the thing for now. Fine, I'll post a proof of this when I'm done. Right. So you just have a power 3 minus 3a square minus identity matrix equal to 0. Right. Yeah, so the following is correct. Look at that. B is correct. So yeah. I don't know whether or not these are correct, but B is definitely correct at least. Okay, very interesting. So to the next question now. How do I even convince you that's the correct thing to be doing? I don't know. I don't know actually. This is equal to 0, right? You could treat it like the diagonal element stuff, but then okay, let me just give you a brief proof of it. That's not actually proof, but just one step in the proof. So, right, you got this stuff. Um, right, just delete all that. So this polynomial, right? It has roots x1, x2, x3, which are the eigenvalues of this matrix. Call this matrix as A, of course. Oh, this is not A. Our matrix A is what? You already know what A is. So this, yeah, the roots of this equation, x1, x2, x3 of this equation, of course, those are the eigenvalues of this thing, And what's an eigenvalue really? What happens like if A times some vector, an eigenvector, if you apply A on some eigenvector, then what happens is like this actually gives us the eigenvalue for that eigenvector or any vector along that eigenvector or even opposite to that vector, whatever. And that times this vector itself, right? Yeah. So this lambda stuff, okay, then this means like A minus lambda I, right? That applies vector is equal to 0. So that's what we did. We just figured out the determinant of this guy, because if there's some vector which is not the 0 vector and you're also mapping that vector to the 0 vector, that clearly means this matrix must be singular, right? It's mapping 2 points to the same point. That only happens for singular matrices. Okay, which basically means that what we just figured out is like having its roots as our lambda values, right? Now, if you can write any certain vector, just say v vector, as let's just say your eigenvectors are v1, v2, v3, and your eigenvalues are lambda 1, lambda 2, lambda 3. Then you can write v vector is equal to lambda 1 v1 vector plus lambda 2 v2 vector. Oh shit, it's not that, sorry. Yeah, you can write it like this thing. You can write as I don't know, a v1 vector plus b v2 vector plus c v3 vector. Then you can apply the matrix on this. Okay, this is actually getting very long. This might be more complicated than what I'm thinking. Fine. So then you apply the matrix on this thing, right? On our v vector. Then that just gives us what? That just gives us lambda a v1 vector plus lambda, sorry, lambda 1, okay, then lambda 2 b v2 vector and so on, right? Yeah. So our matrix, what it's basically doing is that first of all, it's figuring out what A, B, C is, and then to do that, you can think of this thing like, okay, you have this matrix with our column vector, C1 vector, V2 vector, V3 vector. This is not the determinant, it's not the scalar product, it's just the matrix with these column vectors. Let apply on this vector A, B, C, that is actually giving us V vector. Let's call this matrix as P vector, right? Or R vector, or whatever you want to call this, right? So what happens is like P vector times this vector, sorry, P matrix that applies on this vector is equal to V vector. So basically this vector ABC, that is equal to the inverse of V vector. All right. Then what happens is that you're doing this thing, right? So this thing is just this thing, P matrix applied on lambda 1, A1, lambda 2, all that stuff, right? Exactly. Yeah, because P matrix was just this thing, right? Made of column vector C1, V2, V3. Right, but guess what? This thing is just this lambda 1, lambda 2, lambda 3, this diagonal matrix applied on this vector ABC. But guess what? This ABC vector, we know what that is just P inverse V vector. So what you basically get is MV vector is equal to P times, let's just call this diagonal matrix as D. So PDP inverse, right? So our matrix applied on V vector is just PDP inverse applied on V vector. So now I get rid of these V vectors because this happens for any V vector actually. So our matrix can be written as this thing. It's just P, then some diagonal matrix, which is having lambda 1, lambda 2, lambda 3 as its elements, and then P inverse, right? But what that means is that, right, when we talk about this thing, yeah, okay. So our A is just this thing. Our A is PDP inverse, right? But that means like A square is going to PDP inverse applied on PDP inverse. But that is once again just PDDP inverse, which is just PD square P inverse, because yeah. And then A cube would just be, you know, the same pattern for just PD cube P inverse. So then this thing is basically saying like, and of course the identity matrix is just P times P inverse. So you can write this complete left hand side as this thing P inverse, but then between that is sandwiched this thing, the diagonal matrix power 3 minus 3D square minus the identity matrix. And that applied, okay, this is not supposed to happen. So P times of all that stuff, well, that, and then you got P inverse. So this is what this left hand side actually is. And you know, this thing is actually 0 because the diagonal matrix to any power is like, that's the same thing as saying this thing, lambda 1 power n. So the power, right, d power n is just equal to this thing. lambda 1 power n, lambda 2 power n, lambda 3 power n, this diagonal matrix, right? I'm not writing all the other elements because they're supposed to be 0, right? Yeah, and guess what? Guess what? Each diagonal element, right? So when you do this thing, when you do d cube minus 3d square minus I, what you're actually doing is this matrix, this diagonal matrix, lambda 1 power 3 minus 3 lambda 1 squared minus 1, right? Then lambda 2 power 3 minus 3 lambda 2 square minus 1. And then you see the thing, right? The same thing for the third diagonal element as well. And then every other is 0. Right, but guess what? We just said that lambda 1 is a root of this equation. So yeah, like this thing is just 0. So it's a diagonal matrix with all elements being equal to 0. That's our 0 matrix. So this left hand side just becomes this thing P 0 P inverse. So 0 matrix, of course, the null matrix. So this, yeah, is just the 0 matrix itself. And that means it's equal to the right hand side, 0. That's why our A will actually satisfy this equation, right? And now I need to put up a proof of this thing because we already proved that in this little video, right? So that's it. We proved this. Now you can use this without hesitation, I think. Okay, cool. So that means B is correct. I don't know what A or C or D, but whatever. Next question, 42. 42. If AB are square matrices of the same order, then this thing AB dash, what does dash mean? Transpose or something? I guess so. Or does it mean inverse? It depends on how they are using it. I think that it just means the transpose. So AB, that transpose is just A dash, B dash. Yeah, I believe in that. I believe in that, of course. Yeah, like that is actually one thing that we know is correct. So AB transpose is definitely just A transpose, B transpose. But what if it's like inverse? So if it's AB inverse, then that is equal to, B inverse, A inverse, which is not this thing, okay? It's getting weird. Okay, I think A is correct. What else do you have? AB transpose equal to B dash, B dash. If this is transpose, then A is correct. A equal to 0 if determinant of A equal to 0 or determinant of B equal to 0. No, not necessarily, right? If somehow like both have determinant equal to 0, but they are not having this property that they're, yeah, like if it's like, how do I even say this thing? Right, if it's not a 0 matrix, but instead it's the null matrix, then what do you do, right? If A times B is equal to the null matrix and both of them have determinant equal to 0 or something like that, right? Yeah, that would be a problematic thing, of course. What is this thing? I? What? What is this? Just how stupid is this that you're writing I over there and not 1? It's a pure number, right? It's what is this? Seriously. So if determinant of A equal to 1, determinant of B equal to 1, that's just stupid. So D is wrong. C also wrong. It's an incorrect conclusion. That's probably not correct, right? Yeah, definitely not correct. If AB equal to 0, then one of these should be correct. Yes, but if this is correct, then AB is equal to 0. No, that's wrong. It's just plain wrong. Then A is the correct option. Next question, 43. It really depends on what this dash actually represents. I think it's the transpose. Whatever. Okay. AB are 3 into 2 matrices and C is a 2 into 3 order matrix, which the following matrices are not defined. Okay. 3 into 2. Okay, cool. So well, C dash would just be 3 to 2 as well. So that addition, okay, that actually works out. No big deal. A plus, okay, A dash plus B is just not defined. A dash plus B dash is defined. This is defined. This is defined. This one, not really, because it's like 3. Sorry, it's 2 into 3 matrix plus 3 to 2 matrix, which doesn't make sense. So A is not defined. Next question, 44. This matrix is known as antisymmetric or skew symmetric or whatever. So B, and it's also singular, but that's not clear. Okay, this matrix is non-singular if. So yeah, its determinant should not be equal to 0. So just figure out when is this actually equal to single, when is this equal to 0, because it's a linear equation anyway. Yeah, whatever. You are negative 2, negative 3 over there is like negative. What is this 4? How weird is that? It's 2 word. We just subtract that actually. Yeah, no easy connection. We just actually have to do it. We have to do it the proper way, seems. So first thing first, just add this one to that. What do you get? You get this thing. 2 lambda negative 4 0 1 1 1 negative 2 negative 3. Okay, then using this, you can get rid of this thing. Just add 3 3 over there. This is gone. It's just, yeah, of course. So yes, I think that's doable. So what do you get? Just get like 1 1 0 in that case, right? I guess so. Yeah, most likely it's just correct. Then using, you can just subtract this from there. So we get this thing. 2 lambda plus 4 negative 4 1 0 0. And then subtract that from there. It's just, you know, plus 2 in that case. Less 0 over then like 0 1. Makes sense? So yeah, well, lambda plus 2 times this thing is just negative 1. That's equal to 0. So lambda plus 2 should not be equal to 0. That's all it's saying. Yes, lambda plus 2 should not be equal to 0. So lambda is not equal to negative 2. So A is correct. Next question. 46. This matrix is orthogonal, involuntary, idempotent, nilpotent. Okay, what do you have? 1, 2, negative 2, 2, 1, 2. This is weird. It's just 1, 2, and 2 everywhere actually. Except this is negative over there. This maybe this is 1, 2, negative 2 or something. Dot perhaps. Oh, okay, let's actually figure out the dot perhaps. So this dotted with this is what? It's just 0. Yeah. And this dotted with that is what? It's just 2 and then negative 4 plus 2. Actually, that is to 0. Awesome. It looks like it's orthogonal. What about this guy? It's just dotted. It's got 4 minus 2 minus 2 0. Yes. Okay. Yeah. Okay. It's orthogonal. And 1 upon 3. What's square root of 1 plus 4 plus 4 is 3, of course. Yeah. Okay. Got it. This thing is just orthogonal. It's orthogonal, of course. Yep. It's involuntary. This is the inverse of itself. A is equal to a squared or something, right? The determinant is definitely just 1. I think orthogonal is the best description. I don't think it's involuntary or something. Idempotent. Nilpotent. Okay. Well, that's weird. Its transpose is its own inverse. But then the transpose is not itself. So it's not idempotent. But idempotent is the same thing as involuntary, right? I mean, think of it as a function. So then a squared is equal to, no, okay, idempotent is like a squared equal to idempotent is equal to a, which, okay, that's not the thing, right? It's not the thing. Okay, nilpotent, nope. Because that would require this guy's determinant should be equal to 0, which is not correct. Is it involuntary? It's not, because a inverse, wait a second. Okay, a inverse is not equal to a, right? That's the thing. Yeah, because a inverse is equal to a transpose, but then a transpose is not equal to a, so not involuntary. It could be idempotent, but who cares? Next question. We should check, right? We should check whether or not it's actually idempotent. A squared. Oh god. Are you serious? It's like a 3 by 3 matrix multiplication. Just have to do it. So 1 upon 9 and then uh, something nice will happen, right? Yeah. Hope something nice will happen. 1, 2, negative 2. And you got 2, 1, 2. You got 2, negative 2, 1. Oh, it's negative 1. And this applied on itself. I have zero hopes that this is going to be idempotent, but we'll still check it anyway. So what's this going to be? It's the first vector applied on this guy. Just, well, this is like 1 upon 9. So this better be 9. Otherwise, this is not going to help. It's got 1, then 4, and okay, it's not. It's not 9. It's not idempotent. Oh, wait, no. We don't want it to be idempotent. We want it to be... Oh, shit. Right. It's a different thing, of course. For it being idempotent, this should be... Yeah, well, that 1/3, huh? It should be consumed or something. But that's just 1, and then like 1 upon 9 and 1. That doesn't actually make any sense, right? It's the first element is already 1 upon 9, which is not 1 upon 3. So guess what? No, it's not idempotent. Anyway, next question, 47. If A is equal to this thing, it's symmetric, then X is equal to what? So this thing is symmetric, then what's X? Huh. It doesn't matter what X plus 1 is, it's just that these two should be equal. So, X is equal to 5. What kind of question was this? Seriously, why do you ask me this? Let's check this once again. 10 minus 7, 3 is just 7, and then also 7. So B is correct. Next question. If AB are square matrices of order n into n, then A minus B square is equal to. Oh god. No, that is wrong. This seems correct. Let's just try it out. A minus B applied on A minus B. First, A applied on this thing is just A squared minus AB. Then minus B applied on like minus BA and plus B squared. So A squared minus AB. Where's that? Minus AB. Yeah, so D is correct. Next question. Because commutativity is not there. So yeah. 49. Once again, rotational matrix. The following is not correct. It's an orthogonal matrix. Yes, it is. Determinant of A equal to 1. Yes, it's orthogonal matrix as well. Yeah, it is. A is not invertible. It is invertible. What are you talking about? Oh, okay. Then D is not correct. Right. 50. Matrix A is such that this is equal to. Okay. So A squared is equal to 2A. It's like more like saying A squared minus 2A plus their matrix is equal to 0. Zero matrix, of course. Now this thing is the same as saying A minus A squared. You might be saying, okay, this was not commutative and all that. Then how are you so sure it's going to be the same? Just do it, right? Just actually multiply it out. You will see it is actually just that. So A minus identity matrix squared is equal to 0. 0 itself. Well, that's a weird thing. Okay. Very weird. Okay, whatever. Then for n bigger than or equal to A bar n is A power n, you are saying. This is getting weird, isn't it? Okay. Come on, think about it. So it's something that I can do, right? Fibonacci sequence or something like that, right? Okay. It's nilpotent or something. A minus I is good. Yeah, well, it's different. That's very different. Something like a recursion, right? Exactly, just some kind of recursion. I don't like this. Nope, I don't. I wish I had some better way to do this thing. A power n, right? Okay. Could reduce it, yes, sure can, but how is this actually going to be helpful? It's not. You could write it like identity matrix plus A minus identity matrix squared or something. Yeah, that might actually help. Who knows? So I'm considering that. Okay, so let's just say A minus identity matrix that's equal to the matrix B. So just A power n, that's like saying I plus B power n. Like B squared is equal to 0. So then this thing using the general binomial theorem. Right, so actually the binomial theorem also works for this thing. Because although I said matrix multiplication is not commutative, for the identity matrix and some other matrix, it is. So I times P is the same thing as P times I. And that basically guarantees that you can actually, yeah, you can actually use the binomial theorem you used to do. So then this can be written as this thing, identity matrix plus NB plus NC2 times B squared and the thing, NC3 B power 3, so on. Just keep on going. But guess what? B square is 0. And similarly, all of the other powers will be 0 because, yeah, nilpotent. So what does that usually mean? This is gone. Everything is just gone. It is I plus NB, which is like I plus N times of A minus I. So it's just N times A minus of N minus 1 times I. So A is correct. Awesome. Next question. 51. 51 is then A be equal to this matrix. Okay, the only correct statement about the matrix A is. So it's not, yeah, okay, this is like, okay, got it. A square equal to I. Okay, that's kind of weird. getting very weird, isn't it? Might just be correct. Who knows? We just figure out if a is actually equal to I. So what's happening? It's converting x to z. Yeah. We just have to figure it out. So this vector goes into that vector. That's 0, 0. That's just negative 1 over this. Like 1, 0, 0, of course. Oh, it somehow works out. I was that's unexpected, but it somehow does work out. It is actually just 1, 0. Yeah, it is. So in fact, A is correct. Wow, I just did it in my head and it's actually correct. So A is correct. Okay, cool. But I'm just think about it, like the first column vector, well, matrix applied on that vector just gives it like 1, 0, 0. Yes, it does. Similarly, for second column vector, it gives us 0, 1, 0. Then the third column vector is like 0, 0, 1. Because, yeah, okay, that's correct. That's just correct, in fact. So A square equal to identity matrix. A inverse does not exist. It does exist because we just saw that A itself is the inverse. A is a zero matrix. That's just wrong. A is equal to negative 1. That's identity matrix. But that's just stupid. It's not identity matrix. It's different. Okay, cool. Next question. A equal to this thing, then adjoint of A is the mod of that, of course. So it's a 2 by 2 matrix, which means this thing is the same thing as the determinant of A itself. Oh, yeah. So what's the determinant of A? Just 16 minus 6, which is 10. So 10, which is B. What is this? It's like, why is there a line over there? I don't know. So B is correct. Maybe just on my screen, I think. Anyway, B is correct. 53. If three negative are eigenvalues of non-singular matrix A and negative of A equal to 4, eigenvalues of this guy is, okay, eigenvalues of non-singular matrix A. 4 eigenvalues of this. That's weird, isn't it? Yeah. Adjoint of A. Well, think about it. Just think about it actually. Uh, Come on, there must be something that I can do. These are the eigenvalues, of course. Considering you can actually do this, and it's not actually. Oh yeah, you can always do diagonalization, right? Okay, this is weird, but let's actually try it out. So before finding adjoint of A, we actually figure out the inverse of A. So A is this thing. It's just P dp inverse, and now D is this thing. It's just lambda lambda 2, which is 3 negative 2 P inverse. So what's A inverse going to be equal to? A inverse would just be, okay, you got P, then yeah, that was the thing, right? Just that should cancel out and some stuff. Yeah. So then it's just 1/3, then negative 1 upon 2. Right. Yeah, that's A inverse. But we know that A inverse, right, A inverse is just the adjoint of A upon the determinant of A. And the determinant of A is just 4. So our adjoint will be just 4 times of this matrix. Right. Which is what? You got P, then 4 upon 3, and then negative 2. Very weird. So guess what? Yeah, actually this works out. This is the diagonal matrix for our adjoint of A, and because we just wrote it like that. Yes, these are our eigenvalues, 4 upon 3 and negative 2. That was easier than I expected. So B is correct. Next question, 54. If matrix A is equal to this thing and A inverse is equal to 1 upon K adjoint of A, then K is, okay, A inverse is equal to 1 upon K adjoint of, more like adjoint of A equal to K times of A inverse. K is defined as determinant of A itself. Yeah. So K is just a determinant of A. Just figure that out somehow. Ah, it's gonna be a long day. Right. It's got 1, 2, 2 over there. Subtract some stuff out. So what do you get? Just get like 2, 0, 5 or yeah. We'll just write 3 over there. Who cares? I just wanna get rid of some stuff. Okay. Well, think what if I get rid of these two values, right? Would that be a good thing to do? I guess so. Because then I'll be using, yeah, that actually would be a very good thing to do. Just do it. So what do you get? Just get this thing, 310. Um, right. Subtract 2 times of this every base. It's like that's a 0 0 over there. Just -3. This thing is just a negative. Oh, it's not negative. It's just 2 itself. Right. Just 1 1. Now use this to get rid of that guy. Awesome. And now you just, yeah, of course, of course, of course. Positive, negative, positive, negative. Just -1 times this minor. 3 1 2 -3. It's easy. It's -1 times -9 -2. So just 11. K should be 11. So please correct. Next question. 55. The inverse of this matrix. Let's see. What matrix? This matrix. Right? What's the adjoint? What's the cofactor matrix first of all? Just like this guy's cofactor, just -d. Yeah, well, no, it's positive, right? Just d. So it's d. This will have just a. This will have negative. Okay, so the cofactor matrix is just this guy, d a, negative c, negative b, whatever. So the adjoint. What am I writing really? Adjoint of a, that is equal to this. It's equal to a d. Oh wait, no, that's not right. It's dA transpose, right? Yeah, okay, transpose. So dA, you got negative b and you got negative c. Awesome. Okay, what about this? We want the inverse. So for the inverse, you have to divide by the determinant of A, which is AD minus BC. So this thing upon AD minus BC. All right. Yep, that's what I'm saying. So B is correct. Next question. And because this is so general, I think that's the only solution. And look at that. That is so stupid. This thing could be correct, but it's actually touches the adjoint. So this is missing. What about this guy? That's just wrong. Okay, that's it. So exercise 1 done. Exercise 2 has, okay, 40 questions. This one has a lot of questions. 65 or something. Then you got me right. Okay, got it. I guess we'll do exercise 2 some other day. For now, it's done. So I'll do it tomorrow, right? Exercise 2. Okay, and this is it. I'll see you guys in the next video. Bye.